Exponents and Logarithms, Essential Mathematics Skills. Do you know how special numbers are? You probably haven't thought about it. It seems that we take them for granted, but without thinking, we deal with them on a daily basis. In fact, they are so important it would be impossible to live without them. Take yesterday, for example. I stopped at the gas station to purchase 12 gallons of gasoline at a cost of $36. When I went to the store, I purchased a pound of sliced beef from the deli and 2 packages of bottled water, each containing 24 bottles. Each water bottle contains 16.9 fluid ounces. Numbers surround us. We have to watch our bank accounts to make sure we have enough money to live. Every day, we check our bank account to make sure that we have enough money to pay our bills and to pay for the essentials of life. But did you know that 800 years ago, not a single person could add or subtract? Not a single person, including mathematicians. There were no banks in the Western world until 600 years ago. So how did people live? I know what you're thinking. You might not be able to believe this. How could this be true? People must have performed calculations. They paid taxes, they had coinage, they had a currency system, they had economies where money was exchanged for goods and services. But following the fall of Rome, Europeans continued to use Roman numerals for 900 years or more. Try and multiply the following Roman numerals. It can't be done. Why? Because it would be no different than trying to perform operational math using words. You can't multiply the words 104 times 4 like language. Roman numerals are not operationally functional. Not until an Italian mathematician, Leonardo of Pisa, introduced Europe to Arabic numeration, people there couldn't put pencil to paper and calculate numerically. Before Arabic numerals, people had to perform all calculations in an awkward, handheld, non-electric calculating device called an abacus. One had to know what people could use it. Without a means to calculate quickly and reliably, Europe's economy remained stagnated. However, by replacing the Roman system with our now familiar 1, 2, 3, 4 through 10 of the Arabic number system, our ancestors suddenly could do mathematics quickly and reliably. Also, Arabic numbers allowed our ancestors to develop a double ledger system that enabled banking to thrive. You wonder, how could this be? But it wasn't until the Arab society began mercantile trade with Europe that these advanced ideas made their way into a backwards European society. Well into the first millennium AD, Arab peoples were far more advanced in science and mathematics than the Europeans. Leonardo of Pisa recognized this, and that's why he advocated the use of Arabic numeration in a landmark book he published in 1200 AD called Liber Abaci, a book of calculating. Arabic numbers were revolutionary. Every digit in a number occupied a place in a column corresponding with a value magnitude, with each column being a magnitude of 10 times greater than the column preceding it. Thus, there was an order and a direction in a number. It was much easier to demonstrate, actually, than to explain. Take the number 53,462. The 2 in this number occupies the ones column. The 6 occupies the tens column. The 4 occupies the 100s column. The 3 occupies the thousands, and 5 the 10,000s. Notice that each position, moving from right to left, is 10 times greater than the preceding column. So I've written it down in this table below what the number actually means. And what we have here is 2 times 1, which is 2, 6 times 10, which is 60, 4 times 100, which is 400, 3 times 1,000 is 3,000, 5 times 10,000 is 50,000. Now, if we add all these up in a column, as a column, we end up with our number 5,462. Each number belonged in a column of numbers, which then were in essence all added together to represent a single value. Each column had a magnitude and was different from the column next to it by a factor of 10. The column to the left of a number was 10 times larger, while the column to the right was 10 times smaller. It was an ingenious idea, really, since this style of representation allowed for mathematical operations such as adding, subtracting, multiplying, dividing, and more, as we'll see. With this new number representation, marketplace transactions could take place without the need of an abacus. As this new form of mathematics spread, numbers that people dealt with also got larger because they were easier to handle. For example, let's say that we have a bundle of items, and this bundle is 5, and I represented these by these sticks. Each bundle is a bundle of 5 sticks or items. If we have 5 of these bundles, we have 5 times 5, which is in the principle of multiplication, and we know that the result is 25. So if we do as I did with this chart down at the bottom with the number of bundles and the corresponding number of items, when we have 5 bundles, we have 25 items. If we continued to multiply by 5, we would have 5 times 25, which is 125. And if we multiply again by 5, we have 625. These numbers are getting large quickly. And this is called a geometric progression or exponential growth. As mathematicians began using this new number system, they found patterns that could be used to represent values and which allowed them to calculate large groupings more readily. For example, let's take 2 and multiply it like we did with the 5s. 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8, 2 times 2 times 2 times 2 is 16, and so on, all the way. I have a chart here that goes up to 128. If you count the number of 2's that are multiplied together, I have the exponential representation on the right. We have what we call the base, which is the number 2, raised to a power, which is the number of times 2 is multiplied against itself to make a particular number. So when we have 2 raised to the 6th power, it means we have 2 multiplied against itself 6 times, and that equals 64. With each additional multiplication of 2, a superscript was added to represent how many times 2 was multiplied against itself. This superscript was called the exponent. The 2 itself is the base and the number that is multiplied by itself. If we had 5's, we would have fives with these exponents and so on. We can see how readily and simply a basic part of the Arabic number itself is made up of this idea of exponents. Each column is 10 times that of the previous. So, for the number 1,111,111, we have 1 multiplied by the various magnitudes of 10. And these are basically the different powers of 10. So 1 million is 6 tens multiplied against each other, or 10 to the 6 power. The 100,000th place is 5 tens multiplied against each other, and that's represented very compactly with a 10 raised to the 5th power. So in our number system, Arabic number system, we use exponential math to represent a number. We call it a base 10 system because each number in the column is 10 times that of the previous. If there's a number that's in a value or in a column, we multiply that number by the magnitude of that column. For example, 9,000. If we have the number 9,000, it means we have 9 times the 1,000, or 10 to the 3. We note that base 10 isn't the only system that can be used to represent numbers, but it also seems to be the most intuitive. This system is called the Arabic number system because Europeans received it from the Arabs. Not to detract from the Arabs, but it is likely that they were influenced by the Indians with whom they traded before they traded with the Europeans. Other cultures used different base systems. The Babylonians used a base 12 system as well as a base 60. That's why we have 60 minutes to an hour, 360 degrees in a circle, and so on. The Mayan civilization in Central South America, or Central America, used a base 12 mathematics too. As European mathematicians were learning and using the Arabic math system, they also developed representations for patterns that they noticed. Going back to our base 2 numbers, we see that if we group these numbers in different ways, for example, 2 times 2 times 2 as one group, times 2 times 2 times 2, another group, we have 2 to the 3rd times 2 to the 3rd, which is ultimately equal to 2 to the 6th. We can change the way we group these things around, such as 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 2nd power times 2 to the 4th, which is equal to 2 to the 6th, and so on. So we notice these patterns, and mathematicians then developed some basic laws for exponents. Law number 1 is when you have the same base raised to different powers, the result is that base raised to the addition of the two powers. So b to the m times b to the n is equal to b to the n plus m. The same sort of a corollary to that is the second law, where b to the n divided by b to the m is the same as b to the n times b to the minus m, which then is the difference between the exponents, b to the n minus m. Law number 3 is when you have b to the n raised to the mth power, we have b raised to the m times n. We also have two other identities we call law number 4, where b to the 0 is 1. So b to the 0th power is the number 1. And the last law is b to the single power, or power of 1, is equal to itself. B to the 1 is equal to b. These are the 5 most critical rules or laws that you'll deal with in exponents. Summarizing, some base raised to some exponential power yields a number n. Mathematically, this is portrayed with that the equation I have presented here. B raised to the x is equal to n. Now, logarithms are a function that return the value of an exponent as shown above. So if we take the log base b of b to the x, we also take the log base b of n. And using some of the laws of logarithms, we're able to calculate what that exponent should be to raise b to yield the value n. So, like the laws of exponents, there are laws for logarithms, and they're corollaries basically to the laws of logarithms that we've seen, or corollaries to the laws of exponents that we've seen. Law number 1 is the log of base b of b is equal to 1. That really correlates to b to the first power equals to b. Law number 2 is that when you have an argument like b of the function log b of b to the x, we take the exponent and we bring it outside of the log and multiply it against the log. So we can isolate b by itself. Now, log of b, we've seen in law number 1 is 1. So we've isolated x. We'll call that law number 2. Law number 3 is the log base b of 1 is equal to 0, and that is a corollary to b raised to the 0 is equal to 1. The other two, the last two, law number 4 and number 5, those are very critical laws. You find these are used in calculations very frequently. The log of a times b is equal to the log of a plus the log of b. And lastly, the log of a divided by b is equal to log a minus log of b. These are the 5 laws of logarithms. And they have a corollary or correspondence to the laws that we saw of exponents. Now, we have written a book here I've entitled basically Exponents and Logarithms. I'm offering it for free download to anybody who wants it. You can download this thing. I put the link of this PDF book. It's a 66-page book. And it's attached in the description section of this video. So you'll be able to download it for free from a Google Drive. The book presents how exponential math evolved, provides the laws and the rules for exponents, as we've seen, discusses roots in terms of fractional exponents, transitions into how logarithms return exponential values, provides the laws of logarithms, and has hundreds of practice problems, examples, and solved problems. This is a very comprehensive book, and all of this came from a course that I had taken 40 years ago with Dr. Charles Pine. My notes, I still have my notes from that class, and everything that I have compiled in this book came from that course. And it has excellent examples of how exponential math is performed. So I encourage you, anybody who is taking a course in which they're dealing with logarithms, square roots, cube roots, exponents, scientific notation, and so on, to take a look or even download this book, again, for free. So I'd be very happy to receive your comments, and I'll leave an email contact for you to send me any kind of communication if you have a problem, or if there's something that you'd like to have some help with. I'd be glad to do so. So with that, I'll end it here, and I wish you all the best.